All right, thank you, everyone. Hello, everyone, and thank you for attending today. My name is, I welcome to the machine learning at Sadara for quantitative analysis. I am Ziyad Ramadan. I am a principal chemometrician at Sadara. And I would like first to start with Sadara overview. Sadara is a 25 billion USD investment that was a joint venture between Aramco and Dow Chemical. We were the largest chemical plant ever built in a single phase. It consists of 26 manufacturing. They were all built and operating at the same time. We have all 14 plants completely new to the kingdom. There haven't been there haven't been any manufacturing plant that what Sadara these 14 plant. We were also the first mixed feed cracker for gas and liquid. And also we have about 3 million tons of value added chemicals and plastic annually. And I all welcome you to go and look at our website, see what we do, and also encourage you to look at our career site because we always welcome any new talents that are welcome to join Sadara. Please go and visit our website. Okay, today we're going to talk about artificial intelligence. I'm not going to spend so much about it because for the last day, many scholars explain it and everybody knows about it. And this is the topic that we're going to talk today. I will only mainly talk today about the machine learning and how we can use this machine learning in our lab at Sadara. And of course, when you say machine learning, you are automatically inferring to artificial intelligence because it is a subset application of the AI. So they use it, people use it interchangeably. But basically, machine learning is part of the umbrella of the big umbrella of the artificial intelligence, where you have the natural language processing, speech, all different, they are all under the umbrella of the machine learning. But today, we're going to talk specifically in machine learning. AI is not new actually to analytical chemistry. Actually, we were the first research center or one of the first research centers where we applied artificial intelligence in analytical chemistry. And specifically here in this case that we use IAI in ion exclusion chromatography. It's a method that we use in analytical chemistry to separate small bases and acids. And actually at that time, what we wanted to do, we wanted to use artificial intelligence to build an expert system that can help end user how to find the good condition to run an experiment in ion exclusion chromatography to find the best conditions. And at that time, internet was just in the beginning. We didn't have the data that is available nowadays. And actually also the computer power at that time, it was not as we have today. Remember, we used to work with the 486 and it was a revolutionary computer at that time. But this is failed at that time because of the data that we have. And data, again, how we collect the data wasn't in the internet. Even the scientific literature was not even online. You have to read it on paper and you have transfer this knowledge into data. And that was the job of Professor Paul Haddad, who is an expert in this team. And we also collaborated with my supervisor, Bryn Hibbert, and also the Department of Artificial Intelligence in University of New South Wales in Australia. And this was part of my PhD. And in this paper, we used a method that at that time developed by the AI department in New South Wales called ripple down rules, where it actually, you can infer rules from the data, and at the same time you can add data at the end you can augment the knowledge base without you have to repeat everything. And we were very successful at that time. We built it in Visual Basic. And the next step was to test these experimentally by conducting experiments that recommended by the expert system. Of course, you can see here, this is our definition of expert system. I'm not going to go into much of details, but you can see so many words. But the key word is what we wanted that uh, 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 expert system that can replace a specialist, a human specialist in a solution. That was our ultimate aim at that time. Now, machine learning, of course, everybody talk about it, but the key word that I want you to take from this slide, machine learning it's the ability to learn. That's the key word that we need to concentrate in, because if this machine learning has no ability to learn, then it is not a machine learning anymore. It is not even an AI. And it also has to learn from data without putting a programming or equation that you already have. You can help, but at the end, it has to learn from the data. That's the main thing. And then by learning from data, it can identify patterns and also can make decisions. Again, with the minimum human intervention. We don't want to take the human intervention outside the formula, but we have to minimize it as possible, because that's what will be the aim, the final end of AI or a machine learning. And the most important thing that this has to adapt with the new data. Whenever we have a new data coming in, they have to learn from it so that the learning will increase. That's a very important thing that we need to concentrate whenever you do any of the machine learning. Again, the next, sorry. Okay, and the next, you've seen this slides many times, many from our previous speakers yesterday. But the reason that I put this down when you have two types of machine learning, supervised and unsupervised, where and when we use it. And I will give you an examples of my experience of where I did use a clustering and where I use classification and where I use a regression. And also, I'd like to mention that they mentioned a lot of the methods that use or the in these machine learning. I would like to emphasize about two different methods that we use extensively in analytical chemistry: principal component analysis and partial least square. And we'll talk more about it as we go further. But the first example, when do you use clustering? When we use unsupervised. And these methods, specifically principal component analysis, it's a regression method, yes. But again, one of the speakers yesterday talked about what we call the collinearity. And this is a problem specifically in our analytical data, because we have frequencies and we have absorption or intensities at different peaks. And this is a major problem in terms of collinearity. So we have to look at machine learning methods that can help us solving this problem. And that's what we use, what we call projection methods or data reduction methods, or so that it can help us in removing these collinearity. But when we use, for example, PCA, when identifying patterns, it is a very sensitive method for outlier detection. And this is a very important, because the data that you want to use later on in your AI, if it is not clean, you will not have a clean machine learning. And everybody knows about garbage in, garbage out. And one of his examples that use it for clustering and outlier detection, when I was working with in Clarkson University, and we were collaborating with the EPA, Department of Environmental Protection Agency in USA, where we were they have multiple sites where they are collecting aerosol particles when blowing air into a filter paper, and this filter paper sent to the lab and analyzed, so that we were trying to identify sources of pollution. We didn't know what are the sources of pollution are there. And that's why we used unsupervised method to identify what are the sources of pollution. And the reason we use many of these regression methods and try to avoid nonlinear regression or nonlinear relationship like neural network, because again, at that time, scientists think of this as a black box. And still many people think these neural network as a black box, because you put your input and then you have all these weights and all these inner hidden layers, and then you get an output. But how you came up with that output, that sometimes is a mystery. While in these methods, although that it is reducing thousands of variables into a few variables, it still can go back and get the signature what's happening there. So in this example, when we have the EPA, of course, we run PCA, we found the huge clusters, and we were surprised why we have that clusters. And when we went back to the signature of these latent variables that we call it in principal component aggression or PLS, we found that there's a key signature of elements coming from fireworks. And when we look at the samples run on that, it was on the 4th of July. And everybody in the US know what is the 4th of July, where you have many people around the country use fireworks in that Independence Day. So this is a very good technique to check your data. And also, specifically, if you have a spectral data, there are always errors where you make sure that all the spectra that you're going to use it later on, it should be a good spectra. Now, again, this will be an input for the supervised. Once you identify the clusters in your data, then you can assign them and label them, and then you can use it in the next phase, which is the supervised learning. Now, in classification, we use it. I use it a lot in analyzing metabolomic data and genomic data. While I was working at Nestle Research Center in Switzerland, where we were looking at metabolically profiling different groups of people. And in this case, we conducted a clinical study for two groups of men, who one like chocolate and the one who doesn't like chocolate. And the reason we chose men, because we already found women that they don't like chocolate. So based on this, we wanted to see what are the difference between, and we have them on our site. We put them on a standard diet to avoid any variation that not related to what we're looking for. And then we give them chocolate, and half were given chocolate, half were given piece of bread. And then the next one day of it was a crossover study. And the next day we switched and we collected biological sample, blood and urine, and we run it on NMR. And we know what we have, and we try to identify clusters. We found that there are differences between these two groups, and we were able to go back into the NMR, identify key biomarkers that differentiate with this team group. And the interesting part that we found there, and the paper was published and it got a huge media coverage at that time, we found that the key signature for the differences between the ones who like chocolate and the ones who doesn't like chocolate was the gut bacteria. So it is the bugs in your stomach that are responsible for. And again, all these methods, because when we do these measurements, we measure everything. And we let the system tell us which of the key signature that we need to look at to do further studies. And then you can do what we call target analysis. And at that time also, we wanted to use the genomic data, the metabolomic data, transcriptomic data, and go into what at that time is called personalized nutrition. And pharma were looking also at personalized medicine. So this was very powerful tools. And at that time, we use orthogonal partial least square, which is basically another, it is still PLS, but it's using kind of filtering to remove any structural noise to concentrate only on the classes that we have. The last part, which is the regression part, which is here, we were looking at quantity. This is what we are now currently using at Sadara. It is the same thing. Rather than predicting the classes, we wanted to predict the quantity. This is an example, a cup of tea. Now, the question that when we have samples coming to our lab is how much in that lab. And the first priority in this is the safety. we want to measure. We don't deal with tea. That's an example, but we deal with very dangerous chemicals. And we wanted to measure the chemical in a sample without compromising first safety, and also get an accurate and results measurements of the chemical in interest in, for example, here tea in a cup, in the cup that to be prepared. How much is it? Now, there are two ways how you can do it. Either the classical way, where you have to take that sample into the lab and then either do evaporation and either injected it in different different instrument, or maybe titration, whatever, so that finally you get the amount that you were looking in this cup of tea. Or you can use the alternative method, which we will going to explain later, which is, and again, the classical one could take 1 hour, 2 hours, 3 hours. It depends on how the amount, and if you're looking at grams, is different than looking at milligrams, or different than parts per million or parts per billion. Sometimes we are looking at very, very low quantities in parts per billion. Now, the first slide, you will not be able to predict how much is it. But if I present you with this picture now, at least you can give me a number that could be between 0.5 and 0.4. Basically, because now actually what I did, I used an AI. I use your eye as a detector to detect the color of this different cup. And based on that, your mind now were able to find out how much, actually with certain uncertainty, how much of tea is used to prepare that cup of tea. But in chemistry, in the lab, we don't use eye as a detector, we use instruments. And the way how chemicals behave when light passes through them, this is a very important feature that we use it, how the light interact with the physical matter. There are many, many ways how it either absorbs, scatters, all of these. At the end, when we detect, you get at a spectra, this gives us what we call a fingerprint. It is the fingerprint for that chemical, and we use that fingerprint either to identify or even to quantify the sample based on quantity. So this is a very important feature, and we use this data later on in analyzing. And this is one example. We can use other example, like when you put a magnet in the sample and then you analyze it. And the important thing is that you are not measuring one component. In a cup of tea, there are many, and we are sometimes interested in one component, for example, caffeine. So the current machine learning at Sadara, we have, and this is how we do it. You have samples, and it should be real samples, not prepared. You do it in the lab, you measure the spectra, then you build your machine model, and then you have this model that you develop. And then whenever you have a new samples, you run a spectra, you apply the machine, and you get the prediction. And the samples that used for 2 or 3 hours, now you can do it in a very short way, and this helps us in saving cost, and again reduce the interaction of our lab scientists with the chemical, so that improve the safety, because the less interaction with the chemical, the better, that we always recommend it. And of course, we have so many ways to prevent the direct interaction by putting many barriers if they needed to interact with the chemical. But this will help us in saving money and cost. And the beauty about this, that you can put it in your process line. You can put it online, and we have the online analyzer with the PAL team, where they have all the put in different processing in the line, and that this is help us to monitor the process. And is also avoid handling the sample by taking it to the lab if you have inline or outline. And this is automatically will give you the information to the operator so that they can take addition. The only thing in this is that final product, we cannot use this alternative method, because sometimes the certificate of analysis need to be done the classical way. But this is in process samples. It's a very helpful, and many pharmaceutical company, and also at Sadara, we use some of these techniques in monitoring our process. So what is the role of AI in a quality lab? There is a lot of complexity of the samples, and of course AI is a very, very obvious that need to be used. And what we aiming in AI by doing real-time monitoring, predictive analytics, and automatic decision. I will go quickly about hoping that I don't run out of time. Monitoring, we need to monitor, analyze data in real time. And in Cal, in Central Analytical Lab, we receive about 600 samples per day. And each of these samples has almost 4 to 8 analyses on average. And this is a challenge because we want to deliver safely accurate analysis result by using also quality check. This is another top samples that need to be analyzed with high qualities for Sadara operation. These numbers are very important for Sadara operation because they are going to take decision, and this might affect the quality of the product that we're going to sell and also the safety of the plant if these numbers. So we will always make sure that these numbers are high quality data, and that's a very important, and of course measured safely. So we want to use the AI for predictive analytics. Can we use this to enable preventive measures in our lab and also in our online analyzers? We want to constantly measure the LIMS system where we have the data that can help us in take action, and that's what we did in Sadara. We developed an in-house software, and this is all developed by Sadara and used by Sadara, and I'll go through three of them. I cannot do in details because there are some of the IP issue, but Shift Master monitor the flow of the samples, the 600 samples per day. So it monitors the flows, and based on historic data, we can tell if the sample is being delayed and then give an alert to our lab technician so that we can put more resources. Lab Master work with the laboratory operation data that we produce and detect any outliers. QC master used for checking the 300 charts, so the chemists didn't have to look 300 in manually. They can directly direct where is the problem and then address the problem and record what was the problem, because this is a very important that will be used later. Online Shift Master is just combination, and it's an 24-hour dashboard that in our lab where you have it's a big screen and showing. So it's combination of the two. So what we need, the AI, of course, we needed to analyze the data quickly and accurately, and this is a very invaluable in quality control, because the precise analysis is a very important to ensure the reliability of the results. We have a plant master that specifically target certain key parameters in the product, and the data can be coming from IP21 or from the LIMS. You analyze it using SPC and give the operation a quick overview of the plant, where there's a problem, and then they can, this is a very important thing, that they record what happened, and this what we call the metadata, that we're going to use it later in the future to find problems and train the system that can tell us, because analytical data by itself is not enough. Quality data, of course, is not enough by itself. We needed the logbook, and this is the power of AI that can handle what we call it big data, which is consisted of structured and unstructured data. So what is the goal of Sadara? We wanted, this is our aim, a machine learning that can learn from operation and the process data and analytical data for certain prediction of certain outcomes. And we want to do that, we need to investigate factors, variables, because you see, we measure many variables that are available, but are they all important? There are certain key parameters that we need to look at and will tell us the overall variability in the system and identify which has the largest effect. And the data that we put in like the log and the cause and action, this is what we are collecting. Sadara started in 2016, and we have a huge amount of historic data that we are using it currently, and we want to use it for future AI. will be my last slide. This is one example that we did in Sadara, where I cannot go into much of the details, but this is looking at different quality parameters. And we asked at that time the scientists to look at all the parameters in your process and let the system tell us where is the key parameters that are important to understand what happened there. And the system gave us, or the machine learning gave us, what are the parameters that they needed to look at. And it was very helpful because sometimes some of these parameters, they never thought that they would be taking them into consideration, and it was very helpful. So this is my last slide. I would like first to thank you for your attention. And I didn't put technology here because if I'm going to put names here, I will have more slides than what I present today. But this is a teamwork. It's a work. I was chosen to deliver this speech today, but this is the work of everybody here at Sadara. Starting from the lab technician, these are the frontline people who are dealing with these samples every day and analyzing them safely and accurately to provide high quality data. It also from our lab scientists, chemists, envelope chemists, because these are really a very, very smart people who are using a very innovative way to analyze data and find different ways how you come up with the new methods, how we can handle these safely, and how we can analyze the samples. It also, I would like to thank our IT people, the LIMS, who take care of our data and store it and make sure it is available whenever we need it. The quality server, the supervisors, and these are all a dedicated person who are really, they are contribute to this world. Their ideas, their innovative ways, this is all put in the software, what we're developing and what will be later in the future using in the AI. And finally, of course, we would like to thank our management in Sadara, because without their support, this will never happen. Without their continuous support and providing all the necessary resources for using an innovative technique. The bottom line here is this: AI will not take the job of people here. What's going to take the job is somebody else who knows AI. He's going to take your job. Companies, if they don't invest, this is the future. If they don't invest in AI, and Sadara is currently investing a lot in this technology, because history tells us if you don't use the new technology, somebody else will take, and somebody else will take your, and they will have competitive advantages on your company. An example is they're very obvious: Kodak, BlackBerry, Nokia. They all have the technology, but somehow in their mind that they were thinking nobody will move from a film into a digital. They have the technology, they have the IPs, but they didn't use it. They didn't use it. The same thing for Nokia, the same thing for BlackBerry. Nobody, they were thinking, no, nobody will use a phone to browse the internet. They are going to use it only and only for making calls, but people changes. And of course, Sadara is on the forefront of using this technology, and we all proud to be part of this. And thank you for your attention, and I will be happy to answer any questions.